All right, and in this video lesson now, let's look at the substitution method, a very famous method for handling some of the more challenging integral problems or integration problems. Okay, so the method we're doing here specifically is called the substitution method. Okay, and of course, it's the substitution method for doing integral problem. So there are so many different ways how different instructors out there approaching it, and in one entire course of calculus, usually the integral calculus, then some professors decide to introduce this early, and some professors decide to introduce that later at some point. But I feel in my own experience, I highly recommend watching this video after you have seen enough about how to take basic antiderivative problems, how to take basic indefinite integral problem, and then advance on to a little bit further, just right about you have completed the fundamental theorem of calculus. And then this is about the right time when this substitution method is being introduced. So again, so as the bottom line here, in my own experience, I personally feel that it should be successful for students to learn this substitution method right after they have seen the fundamental theorem of calculus, because the point now is that I want my students, my viewers who learn this method, to see this as a technique to handle some of the more challenging problems in taking integral. So at this point, you have learned that this is a definite integral. Okay? And fundamental theorem of calculus say the work is simple. The work is simple. Find the antiderivative. Find the antiderivative. And then once you've had the antiderivative successfully found, then we're going to substitute the operand into the antiderivative, and then do the same. Substitute the lower end into the antiderivative and take the difference between the two. Okay? So fundamental theorem of calculus made it so easy to do this accumulation work. However, going from finding, right at that step where you find the antiderivative of this will sometimes produce a very big challenge. Okay? And so usually right before studying about substitution method, then students are only, in my teaching experience, students are only experienced with basic indefinite integral problem where they take the power rule, the basic power rule, the exponential, very basic exponential function, like say, hey, what's the antiderivative of e to the x? Okay, or what's the antiderivative for 1 over x? Okay, or maybe some of my students who are on track for for a formal math major or on track for engineering major, then you might have heard about sine or cosine function, the trig functions. Then you only know about how to find the antiderivative of those basic functions. But the functions in the beginning here will at some point become challenging, where it looks sometimes impossible to find the antiderivative. And that's where we're going to need to learn more technique to handle those more challenging problems, to find antiderivative, to find the indefinite integral. And then from there, once you've had the indefinite integral, being able to apply the fundamental theorem of calculus is going to be the easy step. Okay? And so for that reason, learning the substitution methods will not change your understanding at all regarding what a definite integral is, what an indefinite integral is. I got to be clear about that. Okay, so it's only a technique to handle the more challenging problem where right at that step where you're finding the antiderivative, where you're finding the indefinite integral, is going to become a challenging problem. That's where this method comes in. Okay, and so now allow me to bring up a problem and you will understand immediately. And so before we really get into that, in the way how I explained just now, then needless to point out, you will find out and you will experience that throughout the entire lesson here, over 3/4 of the time in this video lesson, I am going to focus primarily on applying this method on the indefinite integral, because as I said, that's the biggest step in any of your definite integral work, even though ultimately at the end we want to apply that for definite integral. But the challenge really starts when you deal with those, when you're dealing with those indefinite integral. And so I'm going to spend, as I said, throughout this whole video lesson about a little bit over 3/4 of the time, 3/4 of the time, I'm going to focus most of the examples on the indefinite integrals. And then once you are fluent with those elementary steps, then taking on with the definite integral, apply the substitution method on the definite integral is going to be sort of like on the fly to me. Okay? All right, so now let me introduce a problem. And so allow me to introduce this problem simply as an indefinite integral problem. So let's look at the problem as following. How about an x cubed times x to the 4th? So in parentheses, x to the 4th minus 9 to the 9th power dx. Something like that. So clear. Hopefully it's clear enough on my board to anyone reviewing the video lesson. And so the challenge is here. You got a product, okay? And I did say this in some of the earlier video when I was starting into antiderivative, that there are no direct product rule. And then you can see that there's a power here, but it's a power of an expression rather than the simple power like this one right here. If it's just like an x to the 9, we can find the power easily. We can take the antiderivative or something like this easily. But this is the power 9 of an expression. And inside of that expression, there's other powers. And for this kind of problem, you definitely don't want to FOIL out, because think of the amount of time you're going to have to spend to FOIL out, see, 9 times of this factors. I mean, I'm talking about 9 of this factors multiplied out, and then multiply with, and then distribute out that x cubed right there. It's a lot of work, but it's one possible route. It's just, I'm not patient for going that way. I'm not going to be patient enough to FOIL out, the 9th power of that, and then multiply in that x cubed, because that's the only way so far. So we can't go that way. I mean, it's too much effort going in that way. So now this is what I'm doing. Remember the name of the method here is called substitution method. Okay? So I'm going to start out by, and so for now I'm going to show you how I do it. And then at the end of the problem, I'm going to start talking, I'm going to start giving more discussion. I'm going to start having some more discussion, some more detailed discussion about why I did so. And then I'm going to start pointing out experiences to help you improve when you're on your own problem. Okay? And so for this problem, and remember the method here is called substitution. That means this is what I'm doing. I'm going to pick or choose a substitution. So I'm going to substitute. I am going to substitute this entire expression. And of course, as I said, I will come back and explain when we're done with this particular problem about why I chose that, why I made that. Okay, but for now, I chose that entire expression, x to the 4th minus 9. And I substitute that with a simpler variable. So right now it's 2 terms, and x to the 4th minus 9. It looks complicated, but now I'm going to substitute that away. So I'm going to let all that here to equal 1 variable u right there. Okay? I'm going to let all of that to equal 1 variable u. And so, and how about let me write that into a slightly separate space right there. So u equals x to the 4th minus 9. Okay? That's what and so this substitution point is what I call, I chose that substitution point. Okay, so this substitution right here is what I chose. All right, and so now think about the impact. Once you've made your substitution, think about the impact. Okay, and so here's what happened. The first impact now is that back into this starting problem itself, then it makes perfect sense that at least the whole x to the fourth minus 9 now can be simplified down. I mean, that's one of the goals for doing a substitution. You want to make your expression from starting out from a complicated one to become a much more simplified one. And so now x to the fourth minus 9 now is just all become a u. X to the fourth minus 9, all that lengthy one now become one single u. And then to the 9. But then this x cubed, that's why I kind of accidentally wrote that there. But this x cubed now, we did not substitute for that. We did not substitute for that. So it stayed the same. It makes perfect sense that way. So it's all about we keep track of what we substituted away for. Okay, we're just keeping track. We substitute, and we're responsible for our own substitution. So we're keeping track of what we substitute. So whoever else in the expression did not get the substitution, for now, stay the same. That's my philosophy for this. Okay, and so that's why, as I said, I chose in the beginning for u to equal x to the fourth minus 9. And upon choosing that for the substitution, then yes, it significantly reduced the expression inside of my 9th power here into something like this. A lot shorter already. But unfortunately, outside of that, this guy still did not get a substitution. It's not substituted away. And further, this dx right here still remains the same as well. And now remind yourself here, I've had a different video lesson stating how important this dx is and what it means to the whole expression here. It does mean that the dx expression here is being inner products with all of these guys right here. Okay, so that means we still have about 2 expressions left over that did not get a substitution. And so something like this is dangerous. If you ended up with a problem like this, it's not good, because see, you made it shorter, but then in the end you produce for yourself extra variables. That brings up a sign about danger. Okay, I accidentally say good, but it's not good at all. It's a sign of danger, because now all of a sudden we produced, even though the expression is shorter, but we produce 2 variables. And then if anybody thinks that this is it for the substitution, we're gonna be completely in the off path with that, because I explained in my other video that in a video where I clarified the importance of this d expression right here. So dx here means that is the main variable, and so this is just some other letter out there. So that's not good. It was meant to be some representation of the whole expression that involved x again. So we have so many good reasons to ring a bell that we're not done with the substitutions. There's more to it. So first thing to see in line now is that I did not completely substitute away. Okay? And so now it's time to introduce that. The idea now is that once you have made, and by the way, naming your entire variable here to a new variable's name, that u right here was my choice. You can take your own choice too. You can call that a variable z, you can call that a variable t, whatever that is. But so now in the explanation I was about to say, now, if we decided to substitute and call the new letter of whatever, here it's a u, then everything else that's still relating with the x right here, like say that x cubed is still relating with the x, and that dx here is still associated with x. So after I substituted away that main substitution one, then everything else has to also be in terms of the new variable. Okay, hopefully you got me clear with that. Roll back the video of what I said, or I can repeat again one more time. Once I decided to make a substitution, whatever the name of that substitution I've made, then everything else outside of that direct substitution must also be re-expressed in terms of the new substitution. That means as a plan ahead of time, I want to eventually arrive at something like this, some function, some other function g of u right here, completely in terms of u. And even the d expression here has to be a du instead of the dx. That's what I meant by completely turns everything in terms of u. Okay? So ultimately it all because we substituted the u for this. All right. So that's the plan right here. But see, whatever the plan I'm pointing out right here, there are still a lot unclear thing, a lot of mysteries for anyone watching the video right now. Be patient with me here. We will get there. All I just want to point out now at the bottom line is we are not done with our substitution yet. It's only a very beginning, okay? So now let's hold it there. We're going to have more to do that. I'm not saying that this is wrong, but it's not there for us to be able to move on to the next step. And so now I'm going to go back to the substitution that I have chosen here. I'm going back to this substitution, and this is what happened. If u is chosen to substitute for x to the fourth minus 9, so in the way how the two variables now are related, x with u, then u is a function of x. In the way how it's written, one variable u equals the entire expression of x. Okay? And so in that way, this is how I see it. I can take the derivative du dx. This is the famous derivative symbol for the derivative symbol for u, treating u as a function and x as the variable. Okay, and that equals 4x cubed. This is a constant term, it's gone. So this is the derivative of that, x to the fourth minus 9. Okay. It still didn't get us anywhere yet. I'm pretty sure anyone viewing this video still did not see my intention yet. But now, I had another video where I clarified that. See, when we were only learning about derivative, then I was teaching my students that this was entirely a symbol. Okay? But then believe me, at some point when all of my students who have learned enough derivative works and have seen enough derivative problems, there must be a video of mine right there. Find that video of mine right there and review that for yourself. But there must be a video of mine where I clarify, where I eventually reveal that truth, that at that point, du over dx is now understood as a fraction. Okay? So find that video of mine, that video where I started explaining, and that video, think about the process here. When you were still learning about derivatives, then I call that as one symbol the whole time. Okay, but then as you have finished learning all of the different derivatives, or be experienced enough with derivative, then about the end of your derivatives learning, I started to explain that this symbol was not only a symbol, it really meant it's a fraction of two expressions, the du expression over the dx expression. And each one of these, in that video where I explained that each one of these is the differential of the u, the infinitesimally small u, small change in u, and over the infinitesimally small change in x. That's what d is, the difference. Okay? The infinitesimally small change in u over the infinitesimally small x, change in x. Okay? And so now so now I clarify that this is now a fraction. It's a rational expression of two. It's a fraction of expression of two d expressions here. So what's the good usefulness of that? What's the good usefulness of that? The good usefulness of that now is that from here I can multiply both sides by du. So I can multiply both sides by dx. Okay, I'm moving extremely cautious here. And so once we have allowed that understanding that this is now a fraction, then treating that as a fraction, I can multiply both sides by a dx. So that dx here we cancel on the left-hand side, and so consequently I ended up with like solving an equation algebraically. So du equals 4x cubed dx. Okay, du equals 4x cubed dx. And then we're getting closer. And now I'm going to step one step further. I'm going to divide both sides here by 4x cubed. Okay? And so I am running a little short of space here. So my next space, I'm writing it down here. Okay? So in my next step, you see, dividing 4x cubed from both sides, this is what I'm ending up with. I have now turn my expression into a du over 4x cubed to equals the differential dx. Okay, and again, what is a differential? Find that video lesson of mine, but here I can just briefly remind you that the differential of u here just means it's the infinitesimally small change in u, and the same with the dx. It's the infinitesimally small change in x. Okay, but now if we're treating that as an expression dx, and now we have found an expression that we can substitute for dx, that's the impact right here. Okay, and so now we are ready to complete our substitution work. All right, back to that point where we got hung up with our current interval. Our current indefinite integral is x cubed times u to the 9 dx. And as I was explaining earlier, we're stuck. Okay, we got hung up with this. But now, this dx as one separate expression itself being multiplied with the rest of these factors here in the product. And I have just now on the other board found that dx can be substituted. See, so the whole process is all about substitution. We chose a substitution, and we consequently produced this substitution based on our substitution there. That's the logic of the problem right there. Okay, and so now let's have a look at that closely here. Dx can be substituted by du expression over 4x cubed. Okay, so now I'm going to navigate over to my other board and take care of the problem as following. That dx now gets that substitution. And still, this x cubed right here, I did not have any direct substitution for that yet, or at least I haven't found any substitution for that yet. Let's leave it there. X cubed times u to the 9th. But dx, now we can legally say it's du over 4x cubed. Okay? And so now, at this point, all of a sudden, I want you to realize this together with me here. All of a sudden, I realize I don't need to find any substitution for the x cubed because it's all here. Now, I'm pretty sure you have seen some other clarifications of mine about this du over that. It means it's a 1 over 4x cubed times a du. Okay? And so in that way, we can still see this as a fraction. And so now the x cubed here will get canceled with that x cubed. So it's gone. Okay? And your problem now becomes something like this. U to the 9 over 4 du. But now look at the overall expression again. What good have we brought for ourselves? For a problem in the beginning completely complicated, so complicated, and it was in terms of x. X was the main variable. Okay, and looking at this, something like this, we, at first sight right here, we felt like were clueless completely. And then we made a substitution right here, and consequently that substitution we made as a choice produced another important substitution for the d expression. And then we're going to put the pieces together. So into our original problem, then the whole expression there reduced down to a u to the 9th. That dx expression gets substitute for that du over 4x cubed. And so from that point on, it just easily cancel the x cubed with our current x cubed here that we have not found a substitution for. But so guess what? At this point, we don't have to find a substitution for x cubed anymore, because the good news for us now, we have completely turned the entire problem into a new problem where it's only in terms of u. The complete new variable here is in terms of u. Okay? And then, so now there are a couple of ways you can see this. You can see this problem as an antiderivative problem, or as an indefinite integral of 1/4 times u to the 9 du. That's one way you're seeing it. If it makes it easier for you to recognize the problem. Some people can see this as we can pull the constants outside, okay? and then put the u. That's making it even easier. Okay. Either way, here now you have an answer for yourself. Okay. And so the answer waiting ahead for us here is going to be, and again, as I said, the main point now is that we have now landed into an integral where we can recognize the answer immediately. Or usually in what I always express with my students, this is a trivial integral, the kind of integral where you can see the way where to go immediately. Unlike the one I introduced in the beginning, this is not so trivial, unless we did some substitution, some work on that. Otherwise, the answer is not as trivial as the one we've had here. Okay, and so now this is how trivial that is. The answer is 1/4 times 1/10 u to the 10th plus c. That's how trivial it is. The simple power rule now applies. Okay, but then, or we can rewrite that as 1/40 u to the 10th plus c. Yes, I agree with all that different variations of the final expression. But then we can't stop the problem right here. We can't stop our problem right there. Because think about it again. This is how it works logically. Our problem started out requiring us to integrate this problem or find the integral of this problem, of this function here, in terms of x, As a reminder, I have to emphasize that in terms of x. So we can't just magically leave our final answer in terms of u like this, as an expression, as a function in terms of u. So natural sense now telling us that something is still not quite complete yet. Well, but that's easy to handle now. Let's look back right at our substitution that we made right here. U was equal to x to the 4th minus 9. We made that substitution. Okay? We made that substitution. So that's why now I'm just simply going to replace my u or resubstitute that u back to for what it was. And so now it's going to be, I'm going to need a little more space here. So okay, so that answer now is going to be 1/40. But u can be x to the 4th minus 9 to the 10th. All right, plus c. This is the final answer. All right, so that is our final answer. As a happy point now, the final answer is in the x variable. Okay, and the work here, we came to some trivial integral. That's how I so call it, the integral that you can see the answer so trivially. All right, so there are a lot of, so at this point, well, officially speaking, we're done. And I also highly recommending this, because now as we start learning about different advanced techniques for taking antiderivatives, for taking indefinite integral, you have already know one solid tool to check for yourself whether you have found the correct answer or not. Okay, now let me clear out my part of this board here. So this is what I claim right here. I mean, of course, you follow my video, but I still have to show you this checking work right here. So we say that the answer to this integral is 1/40 times x to the 4th minus 9 to the 10th plus some constant c. That's our answer. How do we know if we didn't make any mistake along the way? Because, of course, now as method gets lengthy, I mean, it gets us to the answer. And then when we came to a final answer, we tend to be a little over happy, and we forgot about whether we have missed any little steps. So one solid technique to check whether you have landed into the correct answer for an antiderivative or for an indefinite integral is to take the derivative of this final answer of yours right here. Well, quickly take a derivative. 1/40 is a constant coefficient. Okay, x to the 9, I mean x to the 4th minus 9, 10 plus c. I'm going to take an overall derivative. So term by terms, that term is a constant, so it goes to 0 when we take the derivative. There's an outside there's inside. So chain rule says, now I'm talking about taking the derivative to verify if we will land into this beginning problem right here. So 1 over 40 as a constant coefficient, it stays the same. Chain rule says we take the derivative of the outside, so it leaves me 10 times all that expression here stays the same, x to the 4th minus 9 raised to the 9. Okay, see how we're starting to get close to there? And then I'm going to multiply with the derivative of the inside, which will give me a 4x cubed. Okay, so 4x cubed, but times 10 is going to be that 4 and that 10 multiplied together. We'll cancel with 40 in the denominator there. So in the end, after some cancellation, we're looking at x cubed times x to the 4th minus 9 to the 9th. We come back to this starting function. So now we knew that this was our correct answer. We knew that we follow the correct work. Okay, and so that's what happened there in this problem. So now we're still not quite done with this problem yet, and so I'm not going to rush into any example yet, because I want my viewers, I want my students to really understand the core understanding of this. And so throughout all the steps I carried out, anywhere I went on that step, on those steps there, I follow my own, I developed my own approach as following. Since the first day I learned about this method, which was a long time ago when I was still a student myself, and over years working on this, this is what I developed into. And now I want my students to take this if you feel it's helpful. And there are other professors out there who explain the approach differently. Okay, but if my own approach, my own guidance is helpful, then you are more than welcome to stay with that. And so the entire process, this is how I see it. The first step is always to pick or to select a substitution. Okay, I got to make it clear right there. The first step is just to pick a substitution. And keep in mind, for the goal of a substitution is that once we substitute it, then some expression is expected to look simpler. That's all it's neat right there. Once you made a substitution, so then some expression is expected to look simpler. That's all. But now look at my instruction here that I'm saying pick a substitution. The word pick right here is quite important. It means there's no right or wrong. In my philosophy about doing substitution method, I never pick on my students about you did a wrong substitution, you did a right substitution. To me, there are no such thing as a right or wrong substitution when you are going specifically for the substitution method. What matters the most is whether the substitution you have picked will lead you into a working path that lands you into the answer. That's what matters. Okay? And so really picking a substitution is on your choice. All right? And then after, and really back to the process that I was working, after I picked the substitution, then I have to ensure, you see, I did all that fancy, I showed on the board all that fancy, the du, dx thingy, and then find the derivative of the substitution. That was all, it was all to ensure this following thing right here. Step 2 is to ensure that, this is actually what I do to myself. I ask myself the question, after I pick the substitution, I'm doing this. I'm going to ask myself, did I wash away? Okay, this is kind of my own term here. I apologize for a little bit of informal, but did I wash away the old variable? Okay, did I wash away the old variable completely? Ask yourself that question, as I've been asking myself this question for years. Anytime I'm doing a substitution problem, and after I have already selected a substitution, okay, I ask myself that question. Why was that? Think about that process that I did again. So let me quickly erase this board. want to make the process a lot faster now. All right, so this is what the whole question number 2 in step 2 is all about. You see, our problem in the beginning was x cubed, the integral of x cubed times x to the 4th minus 9 to the 9th power dx. And then, yes, the substitution I made was, this is a choice. So I said there's no right or wrong about this one. If it works, it will be a good one. If it doesn't work, find another one. Okay? Because, and how do we know if it doesn't work? That's why we follow to the later steps. So if I chose x equals, if I chose u equals x to the 4th minus 9, then immediately, let's set that aside for now. We're going to set that aside for now. Immediately bringing this substitution back into the original problem, it makes your problem to become something like this. X cubed times u to the 9th times dx. You have seen this step in my earlier work. But see, in my mind, when I was explaining, in my mind, when I was going over this problem in that step, outside of explaining in front of you, I was asking myself, did I wash away completely the old variable? And what does that mean by the old variable? The old variable was the x variable, because the new variable is the u. The new variable is the u variable. So tentatively, everything has to be in terms of u. And I also expressed that in when I was going over the steps earlier. Okay, and that's the question I always want to check myself. So I want you to check yourself after you have made your own substitution selection. After you have picked your own substitution, check for yourself by asking yourself that question. Did I completely, or did I wash away? So wash away means you're going to find your way so that your new expression is completely in terms of the new variable, no more of the old variable. That's what it is. Okay, that's what I meant by did I wash away the old variable completely. Okay, so what if we did not? Okay, what if we did not? And that's why if we did not, then we have to find ways. And because here we did not, that's why we got to find that's why this thing was coming along. That's why I was doing this. The du dx thing needs to be for x cubed. And then I took steps solving for the du over 3x cubed to equals dx, so that I produce this extra substitution to ensure that this would become something in terms of u. It was all in the purpose to achieve what I was checking to myself, that whether I have completely washed away the old variable. Okay, so it's a good checking point right there, so that you always got to constantly remind yourself the substitution you made can be whatever, but you got to ensure that once you've made that substitution, you're gonna also change the dx and also find way to change all of the other variables. Anything that remains with the old variable, you did not completely substitute yet. So you gotta pick a substitution so that you can consequently completely wash away all of your old variable. Okay, even the d expression has to also become the d in terms of the new variables you have chosen. That's the idea right there of doing that. All right, and so now once you agree to yourself that yes, I have washed away completely the old variable, then you're going to move on to the next step and check for yourself. So going back to that point, yes, I did. I brought this extra substitution here, and etc., etc. It brought my integral to this final one right here, right before taking the actual integral. The 1/4 u to the 9 du. You see, this was the final integral setup before we were really attempting into getting the actual successful integral. So now when we land into something like that, there's a third step right here that I check myself again. So another question so after this step where now you agree to yourself that you have completely washed away the old variable, then now I bring up the next question. Did I make the integral, okay, mainly the integral problem, did I make the integral more trivial. All right. So what do I mean by trivial? Okay. It just simply means when we started with something like this, we had no clue. And so that's why we needed to do substitution to get things simplified down. And so now, as we have successfully, we made some substitution and we have successfully washed away, or we have completely washed away all of the u variable. The final one right before being able to get the answer, is this a trivial one? That's what I want you to check. Meaning, is this one of those that you are familiar with? Is the final one now provided, agreeing that it's already completely in terms of the new variable, but is this something that you are familiar with? Is this some integral problem that you're familiar with or you have worked with before? Because that's the whole point. Substitution is to simplify your problem down, and look at how simplified this new version. It's the same integral actually. It's the same integral, it's just in terms of the new variable. I gotta make it clear. It's the same integral, just in terms of a different variable. And so in this different form where we express the same variable in a new, the same integral in a new variable over here, is this one here any better? That's the whole idea. Is this one here any more trivial, any more easily recognized, so that we can move on to the next step? Okay, so let me take a quick pause here. The reason this checking step is so important is that, so now, obviously this one was, right? Obviously for anyone watching this video, this one was, so that's why the answer came out so easily. You didn't even have to pull out a calculator or anything like that, or any web resource or anything like that. We came out immediately to 1 over 40 times u to the 9, to the 10th plus c, and then we bring back, and then the last step, of course, it makes sense enough, and I don't even have to put that in as a formal guideline checkpoint like that, but bring that back into the u. So we found our answer. Okay, but in the end, I'm still trying to explain why it's important to that over years I've been checking myself on this particular question here. Did I make the integral more trivial? The reason I share with anyone about this is because I want you to also be flexible on your own. I don't want to say, this is the method, do this. This is the rule, do this. You actually have your own creativity right from the beginning of picking a substitution. I don't want to be the one saying that this you got to only follow my way and that's the only way working. So here's how it happens. So now agree that we got to the answer. But the same problem. Let me now really clarify what I meant by stating or checking myself with that third question. Did I make the integral any more trivial? So here's the thing. So back from step 1, right here. Back from step 1, I said pick a substitution. So really, that means Mr. Professor up here, the instructor up here picked u equal x to the 4th minus 9, okay? You can pick something else different because there are so many different expressions that's complicated enough for you to pick, okay? And so you can, right at the beginning, you can pick this as your substitution. And then now you're going to start asking yourself that same question again. If I pick this, okay, what's going to be the consequence? If I pick this and bring that into my integral. So the u cubed here becomes a u, but we didn't substitute for the x to the 4th minus 9, so let's leave it there, okay? And with the dx. So I did not completely wash away the old variable yet. Obviously, the x is still here. And that's why I'm going to go back to the substitution point here and say du dx equals 3x squared. That's the derivative. And just now, as you have learned that technique earlier, now we are seeing this as a fraction. So I can start solving for dx in terms of the other variables. So dx here, a little bit of algebra, dx multiplied with 3x squared and dividing both sides by 3x squared, I'm looking at du over 3x squared. This is completely the algebra after that derivative step. And so now I'm going to substitute dx with the Okay, so u times x to the 4th minus 9 to the 9th power dx now can get substituted by du over 3x squared. Okay, we washed away more x variable, more o variables, but there's still some o variable left. And so in this route right here, keep trying. I get impatient. I got impatient here, so I stop here. But who knows? There are some people who are more creative in algebra than me that can even advance further. So here we are still stuck with that. Check question number 2 right here, because if that was me, I still have not successfully got past that point. Stage 2, did I completely wash away my old variable? So who knows? Anyone viewing this video is highly recommended to follow different paths right here and find out for yourself. Who knows, there are brilliant minds out there who can handle this thing and completely wash away the x variable from this point. I'm not patient enough to go that path. And so that's why it rang a bell for me to not go this path. It's just a path, one of the paths out there. I'm not saying right, I'm not saying wrong. It's just me. I'm not patient enough to go with that path because it takes me longer to completely wash away the old variable. It's just me. Okay? And so that's one choice, a little story to share. What about? So I gave up, but I'm not saying that viewers who are watching this video have to give up with that method. You are more than welcome to explore. Okay? Same problem again. Pick a substitution. The substitution in the beginning could be just simply x. It's a substitution. You can choose to substitute whatever expression you want for the new variable. Okay? So you do this. Then yes, your du dx is simply just 1, or your du equals dx, because now seeing that as a fraction, you can multiply both sides by dx, and hey, here we go, dx equal du. And we now have found also a substitution for dx as well in our expression. So that means this problem becomes the following. Every x here gets substituted by the u variable. So now it becomes u cubed times u to the 4th minus 9 to the 9th du. Believe it or not, that's what it is. So as far as picking a substitution, we did. No one saying right or wrong about that. Checking your own question. Did I wash away the old variable completely? Yes, I did. It's a good checkpoint. And let's move on to checkpoint number 3 right here. Did I make the integral any more trivial? For that question, did I make the integral any more trivial? It looks just exactly the same. So I didn't really go anywhere. And so this is not a working path for me. Okay? And so in that way, again, I just want to emphasize the point that there are no right or wrong for choosing. And of course, that's why later on after this discussion, I am going to give examples, so that through the examples, you're going to start forming into some experience about how to pick a good working one. But in the end, outside of those experiences, there are still brilliant minds. I've had students in my past quarter who came up with brilliant technique to go with substitution. I highly recommend any of you learning from this video lesson to be creative on your own about that. I don't want you to be tied down to any specific path that anyone has gone through. Maybe it's a good thing that you go with a majority, but at some point you can also think outside of the box as well. Okay? And so that's the whole point I'm trying to say right there. There are no such thing, or there is no right or wrong about a substitution method. First, you pick a substitution. No right or wrong about that. That's your choice. And so, as a matter of fact, when it comes to when I grade my own students' exam right there, I will never pick on them on this particular step on whatever substitution they pick. I respect them. What matters, do they know how to develop from where they picked to the rest and made it successful and landed into an answer? That's what matters. Okay? And so this is the majority, the major understanding of the substitution method. Okay? So now we are ready for getting into the actual example. So let's erase this out. All right, so now we are at example 1. Okay, so let's evaluate. Okay, so I have made for my own lecture notes here a little bit. I have prepared a few problems, and I hope you will learn something good about throughout these problems I've prepared here. So there's an x plus 2 being in product with about an x squared plus 4x minus 9 to the 4th dx. Okay, so x is the old variable, and of course something like this, we have no trivial answer, right? We have no clue where the next thing goes. So the best way is find a way to substitute, find a substitution so that we can simplify some of our expression here, make it shorter, make it more simplified. Okay, and so now for the practicality, of course, in the philosophy I was explaining earlier, then that's for you outside of the class on your own time. I encourage you to love math. So start spending your own time exploring different ways to substitute. But as an example, allow me to introduce the one that in my experience been working out the best for me. And then from there you're going to start drawing out some experience, and then on top of that you will apply your own creativity into solving your own problem as well. Okay? And so it's not really that I brought up these problems for you to have to believe only in the way this man teaching on the computer screen here. So I would choose, and U is not the only letter's choice. How about let's call that a Z? I just want you to be flexible with the variable's name. So I'm going to choose Z as my substitution to be this whole thing, x squared plus 4x minus 9. Okay, this is how I see it. It just simply caught my attention that the whole x squared plus 4x minus 9 is inside a power here, inside a power. Okay, and so I'm just gonna pick the whole thing right there. So x squared plus 4x minus 9. Okay, and so after picking that, then let's start putting some pieces in place right here. If we substitute that for Z, then the whole thing inside the power here is going to become a Z. So it's Z to the 4th. Okay? But the x plus 2, we did not have a substitution for that. Let's leave it there. So it's x plus 2 in products with Z to the 4th. And the dx still did not get a substitution for that. Just like how I have done in that introduction problem. Okay, but now we still can move on further from this from this substitution that we picked. Okay, and so that's why from here I'm going dz dx. This is the derivative of treating z as a function, the derivative of z in terms of x. All right, so now that is going to be 2x plus 4. Okay, that's my derivative dz dx. And then just like how I explained earlier in the beginning of this video, or you can again find my formal video. It was also a short one where I formally explained where was that historical point where I started showing you that this can be understood as a fraction outside of being just a symbol. Okay, more than just being a symbol. So find that video there if you want to have that detailed learning. Otherwise, you can just start accepting that from the beginning of this video lesson as well. But now taking this as a fraction, then we can start solving for dx. That's one of the good key step as well. So now I'm a little bit short of space here, so I'm going to multiply dx to both sides. And then divide instantly, or maybe I shouldn't rush like that. So dz equals the 2x plus 4 times dx on the other side. Okay, and so in that way I'm going to divide both sides by, so I'm going to open a little more space here. Okay, so that means dz over 2x plus 4 is equal to dx. All right, and so now of course if anyone viewing this video is already strong in algebra, then you can simplify some of the steps here. I mean, you can fast forward some of the steps here if it's a little too lengthy for you. Okay, and then now I have found a substitution for dx expression. Now I'm ready to put more pieces, more substitution pieces into my beginning integral. And again, as I said, 3/4 of this lecture is all about handling the substitution methods on an indefinite integral. It has been indefinite integral the whole time. Okay, x plus 2 did not get a substitution for that yet. But then here it's z to the 4th times the dx now. The dx now can be substituted by dz over the 2x plus 4. That's the whole thing. And so dx is dz over 2x plus 4. I put that in parentheses just to indicate that the dx was supposed to be here, but now I replaced that with the whole dz over 2x plus 4. And so look at how useful that is for us now. In the next step, it now becomes, okay, so I see an x over 2. Okay, still did not get a substitution for that. Z to the 4th times, now it's a fraction, or it's a product of 1 times dz. There are so many ways that you can algebraically understanding that now. You can understand that now. So 1 over 2, and see, common factor of 2 in the two terms here. So how about 2 factored out and x plus 2 in parentheses, and then multiply with dz being a separate out. But now that helped me recognize that the x plus 2 here can be cancelled. Instead of searching for another substitution for that, we can cancel it away. Then it's going to be out of our expression. And so after doing this, here's what's going to happen. We reduce down to the integral of z to the 4th over 2 dz. Okay, and then many textbook writers, many textbook authors and professors teach students to write it as a 1/2. I can do that too. I can also encourage my students to do this. It's the same as a 1/2 because it's a coefficient anyway, right? So 1/2 times the integral of z to the 4th. This really comes straight out from the constant rule, the constant multiple, the constant coefficient rule that I've introduced back in the days when we were doing the derivative, the antiderivative rules. Okay. And so now, see, just to remind anyone about the checking steps I was doing. When I made my substitution, there were no right or wrong, but right at that point, substituting the first substitution into the expression, I asked myself that question: did I completely wash away my old variable? Obviously not. And there, especially the dx is still here. And so that's why I went back in here and find my way to substitute for the dx. And now the dx can be substituted by that. And then I came to this point, and then I asked myself that question again: did I wash away completely my old variable? Because there's still some extra here. So the question in step 2 is a question that you can ask yourself multiple times. You keep asking yourself until you completely wash away the old variable. So I keep asking myself and keep improving it. At least there were ways to improve it. There was way to improve it, and to the point now that we landed in here, where I answer yes, I completely washed away all of my old variable, the old variable. So even the d expression here is in terms of the new variable z right here. And now I ask myself the third step, the third checking point question right here: is this a trivial? Did I make my problem more trivial? It obviously is. It is a trivial answer here. So the answer here for that is going to be now 1/2 constant coefficient times 1/5 z to the 5th plus c. All right. So, but then we shouldn't stop at the final answer being in terms of z, because our answer in the beginning, our question in the beginning was in terms of x, and so that now means this is going to be a 1/10, okay, times all that x squared, allow me to write a little bit smaller here, plus 4x minus 9, all that there to the 5th power, plus c. That is now our final answer. Okay, and so that's how we carry through the step for a problem. So the experience I want to show my viewers, my students, is that, so anytime you see an expression being trapped inside a high power like that, okay, I'm not saying that whatever I'm showing here will work 100% of time, but it works about over 90% of time. Pick directly that expression. Pick directly that expression, not only one term, not only two terms, the whole expression being trapped inside a power. Okay? Then work it out. And the reason I say what I'm saying here is not working 100% of time, of course, because that's why there are always a room for you to explore your own creativity out there, because there are still challenging problems out there. There could be a problem where there are two different high powers. Okay? But believe me, I've taught calculus long enough to the point that I even understand that the textbook authors, standard calculus textbook authors come up with problems for their students to be able to go through. So it will always contain those little clues and tricks somewhere here and there for you to easily recognize. So I designed these problems that came out right from textbooks here and there. Okay, it's not like a problem that came out from like a Putnam exams or something like that, where it requires your super creativity. All right. And so experience of mine now is that anytime you, a lot of time, I shouldn't say anytime, how about a lot of time you see a big expression being trapped inside of a high power, pick that one, okay? And then, but whatever I said there should not be something that stops you from trying your own creativity, but keep that, outside of the class, because, that's only for when you're on your own time and you practice and you create, try to come up with more creative solutions. Okay? All right, so now that was part A. So I'm going to look through another one. And actually for the same example here, I want to purposely introduce quite a few the little problems in here. All right, so in part B, and now I have an integral as following. How about t cubed minus t, okay, inside of a fourth root. And now there's a fourth root, and then there's a t to the fourth minus 2 t squared plus 5. All right, so that's my integral, and of course this is dt. You see, so just like how I have explained in some other videos about the importance of this d expression, our problem here is an integral in terms of t. And so the d expression here has to agree with that. And that's why the whole time that I was doing that, it's also, see, once we changed from the main variable x to something else, then we have to ensure the d letter, the d expression has to be consistent with the new variable. And that's why. Okay, that's another part of the reason why there was that checking question number 2 right there. Did I completely wash away my old variable? And that's the whole point. And so now I am going to choose I'm going to go back to u, okay, to be equal to t to the fourth minus 2t squared plus 5. Okay, and so from that point, I can see that immediately I can start doing some substitution. It becomes t cubed minus t. That part at least stays the same for now, because I did not find any substitution for that. I picked a substitution on this, and then multiply with fourth root of u. See how short it gets now? Okay, and dt. Because dt I didn't find an expression, a substitution for that. So now it's time that we put on that checking question right there. Did I completely wash away the old variable? I did not. I have not yet. So that's why we're going to go back to this substitution point and start developing further. So du dt, because now u is a function of t, so that is the derivative of u du dt, being 4t cubed minus 4t All right. And then so yes, a little bit more algebra. Du will equal 4t cubed minus 4t times dt. And so that means du over 4t cubed minus 4t is to equal dt. And so at least now I've found some more substitutions. I can now substitute dt away with that expression, which now involves some du. So it's getting there. It keeps getting better. It keeps getting better. So now I still have not found any substitution for the t cubed minus t. But let's just leave it there. Be patient, because as I said, that question I put in step 2 where you check yourself. You can ask yourself that question multiple times. Now multiply with 4th root of u. This dt now is the same as du over 4t cubed minus 4t. And that's what I'm doing. Okay, and now I can see that this denominator here, 4t cubed minus 4t, has a common factor of 4. So that can become some good plus for us here. So I am now going to get on my other board. All right, so now with my current problem right here, I can recognize that the t cubed minus t here, okay, and then there's a 4th root of u. Now I can recognize here that it's a 1 over 4 times t cubed minus 4t, and then there's a du here. Okay, so now see, in what I explained earlier, I recognize there's a common factor here. So now I can go t cubed minus t, 4th root of u times 4 factorial t cubed minus t du. And now everything is so clear. Even though I keep checking myself multiple times that did I wash away the old variable completely? And at this point, now I feel like I'm ready to wash away the old variable completely. That is now completely be gone. I made my cancellation stroke a little too strong like that. Okay, so now I have left behind for me. I'm going to write that a little bit closer here so I'll have more space for myself later to write the final answer. Okay, so now canceling that away, it gives me this. It's a 1/4 4th root of u du. Okay, it's supposedly a 1/4 on its own, so I write it as a coefficient here. Or you can write it all as a 4th root of u over 4. It's the same algebra expression right there. Okay, and then now I answer that question of mine. I completely washed away the old variable. And so now it's time to move on to the next question. Have I made my integral, did I make my integral more trivial? Okay, it is trivial because this is just nothing but, well, in what we have learned already, we can rewrite this as u to the power 1/4 du. So in the end, it's a root, but, and allow me to flash back a little bit. So right from this, and I'm attempting to make that connection to my explanation in part A earlier. I chose this one because in the same reasoning, the same experience I've had. It's a 4th root. Maybe there are still viewers out there who don't like roots, but I see roots as a power as well. So this whole expression here, the way how I see that is as following. The whole t to the 4th minus 2t squared plus 5 is being trapped inside a power again. Maybe I said high power earlier, but that doesn't have to be high power all the time. It's just basically some power. So that's why I picked the whole thing inside a power. So the whole expression inside a power, or the whole expression inside of a root, because a root is a fractional power. I picked that and looked at how successful it gave me so far. Okay, and so, but still in the end, it worked just about over 90%, but there's still about a room of 10% that's left for for your own responsibility to be creative out there. All right, but now wrapping up this problem here, then my final answer is going to be, see, recognizing fourth root of u as a 1/4 power of u, then the answer is ready for us. Now, it's equal. All right. My next step is a 1/4, the coefficient. I'm going to multiply with u to the 1/4 plus 1, which is the 5/4. Okay, and then 1/5. All right, plus c, which is the same as, okay, all of that together algebraically. You can quickly pull out a paper and sand pencil to do the math right here, but it's now going to be a 1/5 u to the 5/4 plus c. Okay, so that's the current answer right now in terms of u, and that was one of the trivial integral. And then now we just can't stop at a final answer in a completely new variable like that, so we have to bring back whatever we substituted for u right here. So u was a substitution for all that t to the 4th minus 2t squared plus 5 like that. All right, so in that way, now I'm ready to complete our answer. 1/5, and then in parentheses, okay, t to the 4th minus 2t squared plus 5 being raised to the 5/4 power plus c. And that's what it is. Okay, and so that's our final answer. All right, and so now, after about 2 problems in example 1 that I'm going really side by side and so close with the guideline I've had on the board right there, then allow me for the later problems, even though the later problems, even though in the same example here, I'm going to start speeding up the steps and allow you to follow the guideline check, but I'm not going to keep referring back to the guideline checks as closely anymore. Okay.